Chapter 23, Alternating Current Circuits. So up to this point, we've looked at a number of circuits, but they've always been direct current, where it's connected to a battery and the current flows in a single direction. We started doing that way back in chapter 20, but we had to wait until chapter 23 to get to alternating current circuits because we had to learn all these ideas about electromagnetic induction, because with alternating current circuits, that's going to create some interesting effects that look a little bit different than the circuits we've seen thus far. Let's take a look. Our first section is focused on capacitors and capacitive reactance. But before we get to capacitors, we can start with a resistor, because a resistor, it turns out, is the simplest form of an alternating current circuit. So if we have an AC source here, it's shown with the sine wave, and note instead of having a single value of the voltage, it's the peak voltage times sine of 2 pi the frequency times the instant in time. That tells you how the voltage is being applied, and that's being wired to just a resistor. And when we have just a resistor in an AC circuit like this, we have the equation that we've seen before. The RMS voltage is equal to the RMS current times the resistance. Ohm's law, V equals IR. And this is true regardless of how we adjust the frequency F of how quickly the current switches back and forth. So that's what this graph is showing, that the resistance R stays at one constant value even if we adjust the frequency of our AC source. This sounds pretty straightforward, and indeed it is. Where things get more interesting is if instead of having a resistor, what if instead we put a capacitor in our AC circuit? Well, when we put a capacitor in our AC circuit instead of a resistor, the capacitor has its own effective resistance, if you will, and that's known as the capacitive reactance. So it's the capacitor's version of resistance. And sure enough, it follows Ohm's law in a similar fashion, right? Where the voltage is equal to the current times the capacitive reactance, X sub C instead of the R. So the reactance is X, and then C is the subscript for capacitive, because we're talking about a capacitor. Now, the interesting thing about reactances like this is that they actually do change depending on the frequency of the source. So the way you calculate the capacitive reactance is as shown. It's 1 over 2 divided by pi, divided by the frequency of the source, and divided by the capacitance, C, of your capacitor. And if you calculate this out with your SI units, then the units you'll get for the capacitive reactance will just be the same as that of resistance. They'll be in ohms. So there are some definite parallels to resistance, but unlike resistance, where it has a constant value for all frequencies, pretend that line is purely horizontal, the capacitive reactance starts with a very large value at low frequencies and goes down to almost no reactance as the frequency gets higher and higher. Let's see how this plays out in an example. So example 1, a capacitor in an AC circuit. The capacitance is 1.50 microfarads and the RMS voltage is 25 volts. What is the RMS current when the frequency is A, 100 hertz, and B, 5,000 hertz? So in this chapter, we're introducing a lot of new terminology. And so one of the most challenging things with these problems is identifying the different variables. So I encourage you to do that with every problem, but it's extra important in this chapter to be able to name what's what. So we first have this 1.5 microfarads. Now we have two different variables related to capacitance, to capacitors, right? There's the capacitance C and the capacitive reactance. This is indeed the capacitance alone. There's no reactance mentioned, and it's in farads, not ohms. So it is our standard C. this defines the capacitor itself. We also have is 25 volts, which is our V RMS. And what we're looking for is our RMS current. And if you were listening and saying, hey, capacitance, that's similar to resistance, then you might be led astray into going, hey, we can just do Ohm's law, right? V equals I times C, right? There's a problem here, right? What's the problem? Ohm's law doesn't work with the capacitance. It works with the reactance, the capacitive reactance to be specific. So even though I was just trying to X out the equation, it actually worked for the X, which is what we'll actually use here, that we can only write Ohm's law, V is equal to I times the capacitive reactance. We know our V, we want to find I, so if we can just get this capacitive reactance, we'll be good to go. And we have an equation for capacitive reactance, right? Capacitive reactance is equal to 1 divided by 2 pi, divided by the frequency, and divided by the capacitance, which we already identified. And that's where it's really important to note that was only the capacitance, and it isn't yet the reactance. So we know C, the only thing we need now is the frequency, and we can get that frequency for part A and B, which is just 100 or 5,000 hertz. And with that, we will be good to calculate away. So let's see how those calculations go. Right, for A, we have the capacitive reactance equation with 1 over 2 pi Fc. With both of those plugged in, remember micro prefix is 10 to the minus 6. Hertz is already our SI unit, and farad is the other SI unit of capacitance. And as mentioned, if you're working in those SI units, your resultant units are just the same as resistance. They're in ohms. And if you plug this in properly, you should get 1060 ohms. One note, I encourage you to actually try this with your calculator. Make sure you do get the right answer, because I've seen it's really easy to plug in 1 divided by 2 and then put in times pi into your calculator, right? And in your head, you're down here and you're like, hey, it's 2 times pi, right? But unless you put the parentheses there, you'll end up multiplying by pi and you'll get a very different answer. So it's worth double checking that you can do that calculation properly in your calculator. Solving for current is just the RMS voltage divided by our capacitive reactance, which comes out to a fairly small 0.0236 amps. In contrast, in part B, instead of working with 100 hertz, we're going to up that frequency to 5,000 hertz. So this is 50 times larger frequency. And as a result, our capacitive reactance is a factor of 50 smaller. Instead of being 1,000, it's 21.2 ohms. When we then plug that in to our current equation, we find that our current is now much larger, 1.18 amps. It's 50 times bigger. So this highlights what this equation is trying to show, right? That in part A, when we have a small frequency, we get a huge amount of capacitive reactance. That's this region of the graph, where it's a really low frequency, but a high capacitive reactance. In contrast, in part B, we now have a very large frequency. So we've moved to the right on the graph, and as a result, we have a very low capacitive reactance. So we're over here in this region. And if you have less capacitive reactance, you'll get more current, just as we saw with resistors. So that's the first interesting effect of adding in an AC circuit. The next one has to do with the phase of the voltage and the current. So we're going to start with our purely resistive circuit where we just have an AC source and a resistor. And if we look at a graph of the voltage and the current, we'd find that they are moving exactly together. This is said to be in phase. So when the voltage is at a positive peak at point B, the current is at a positive peak at point B. When the voltage is 0, the current is also 0. This matches our perhaps most natural intuition that if we apply a voltage and if we apply the largest voltage, we'll get the largest current. Cool. It turns out it's not this way when we have a capacitor instead. So when you have a capacitor in the circuit, the current leads the voltage by a phase angle of 90 degrees. What does this mean? Well, current here is shown in red and voltage is in blue. And so when the voltage in the source reaches its peak at B, there's no current flowing. And that's because that's when the voltage is maximally charging the capacitors. The capacitor is fully charging up, and then it blocks all the current when it's fully charged. But then, as the voltage in the source drops off, down here, going from B to C down to 0, the current starts to kick in going the opposite direction, thanks to the capacitor. So you see this shift, this offset, that the current is leading the voltage and they are just out of phase by 90 degrees. Another interesting and important conclusion is that the average power and thus the also average energy used by a capacitor in an AC circuit is 0. So we got average power in a resistive circuit and it was definitely not 0. But for a capacitor, it's not using any power. And that's pretty nifty. Now, trying to draw these sine curves next to each other and just slightly offset by 90 degrees, it's really hard to actually draw that out. So there's another way to represent this difference in phase. And the way that we use that is a phasor model. So the phasor model is conveying the exact same information of the past two slides, but with arrows instead of drawing the squiggly sine waves. So we have the voltage and the current that are represented instead of sine waves by rotating arrows, which we call phasors. I know this is a lot of weird terminology, but just keep your phasor set to stun and enjoy the surprise, right? So we have the voltage in blue and the current in red. And these rotate around with some frequency f. So the speed of their motion is this 2 pi f times time. Now, why does this rotating arrow, how can it possibly relate to that sine wave that we had before? Well, let's sketch the sine wave so we have a reference. Right, so there's my axes as a function of time. And then I can draw in my voltage in blue, and I'll just do the resistive circuit because it is easier. So I have the voltage, and then current I'll do in red. And it has a smaller amplitude, but it has the exact same phase here because it is a resistive circuit. All right, so when we do this plot, if we want to get a single value at some instant in time, then we look at a very vertical line and say, okay, at this particular time, t1, the current has so value, the voltage has this other value. Boom. The way that we read the phasor diagram is we say at some instant in time, we take a snapshot of these rotating arrows. They're literally going around in a circle. we're going to take a snapshot of the vertical component of the phasor, and that will give us the instantaneous value of the voltage or current. So the voltage phasor would be up to, say, here. I'll keep it at blue. So that's our instantaneous voltage. So it's not V sub O, which is the peak voltage, it's some instantaneous one. Similarly for the current, the instantaneous value is the vertical component of it. So how much of it is shadowed onto there. And so that will be I, again without a subscript, because it's just the I at that instant, it's not the peak value. So with this phasor, we see that because the blue and the red arrow are drawn right on top of each other, they're in phase. There's no phase difference between them. For the capacitive circuit, because the current is leading the voltage by 90 degrees, we rotate the current 90 degrees ahead of the voltage. So it's like it got a head start. So if we drew a current initially going up and voltage to the left, they would then just continue to rotate together, right? It's like the voltage is chasing the current, but the current keeps moving too, like a dog chasing its tail. But with these, it still would be that we'd look at the vertical component to get the instantaneous value of the current or of our voltage. So this is a helpful model to be able to draw different circuits and be able to represent what is going on in the circuit. And we'll see how this model can help us when we start building more complex AC circuits. But before we get to more complex AC circuits, we'll need to introduce another circuit element. So stick around.